Temper embrittlement damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of temper embrittlement. Based on API 571, temper embrittlement is the reduction in toughness due to a metallurgical change that can occur in some low-alloy steels as a result of long-term exposure in the temperature range of about 650 degrees Fahrenheit to 1070 degrees Fahrenheit, 343 degrees Celsius to 577 degrees Celsius. This change causes an upward shift in the ductile to brittle transition temperature as measured by Charpy impact testing. Although the loss of toughness is not evident at operating temperature, equipment that is temper embrittled may be susceptible to brittle fracture during startup and shutdown. Temper embrittlement is a phenomenon that occurs primarily in certain types of steels, particularly high-strength and low-alloy steels, as well as some other iron-based alloys. It is characterized by a reduction in toughness and an increase in brittleness after the steel undergoes a specific heat treatment or prolonged exposure to elevated temperatures. Temper embrittlement mechanism. Number 1 is heat treatment. Temper embrittlement typically occurs after tempering processes, especially in the range of 300 up to 500 degrees Celsius or 572 up to 932 degrees Fahrenheit. It is often associated with materials that have been quenched and tempered to achieve high strength. Number 2 is element migration. The embrittlement is largely due to the segregation of certain alloying elements, notably phosphorus, and, to a lesser extent, antimony or tin, at the grain boundaries. These elements, when present in small concentrations, can accumulate at the boundaries during the tempering process. Number 3 is grain boundary characteristics. The accumulation of these elements alters the mechanical properties of the steel. The enriched grain boundaries become weaker and more susceptible to fracture, leading to a loss in ductility and impact toughness. Temper embrittlement effects. Number 1 of temper embrittlement effects is reduced toughness. The steel loses its ability to deform plastically under stress, which may lead to catastrophic failure instead of yielding. Number 2 of temper embrittlement effects is brittle fracture. Components may fail suddenly under stress, leading to brittle fractures that propagate rapidly without significant plastic deformation. Number 3 of temper embrittlement effects is diminished performance. This type of damage can significantly affect the performance of components in applications such as structural engineering, pressure vessels, and critical mechanical parts. Understanding temper embrittlement is crucial for engineers and material scientists, particularly when selecting materials for high-stress applications or in environments that may subject steel to tempering conditions. Proper design, material selection, and processing techniques can help prevent this damaging phenomenon, ensuring the reliability and longevity of components. Affected materials of temper embrittlement is a degradation mechanism that affects certain alloys, particularly low-alloy steels and some high-strength steels, during tempering processes after hardening. The primary materials affected by temper embrittlement typically include: Number 1 is low-alloy steels. These steels are often used in structural applications and can exhibit temper embrittlement when subjected to specific heat treatment processes. Number 2 is high-strength steels. Certain high-strength steels, particularly those containing elements like nickel, molybdenum, and chromium, can become embrittled upon tempering. Number 3 is martensitic stainless steels. Some martensitic stainless steels can also experience temper embrittlement, especially those that are subjected to high-temperature tempering. Number 4 is low-carbon steels. Although not as common, low-carbon steels can also exhibit temper embrittlement under specific conditions. The mechanism behind temper embrittlement generally involves the segregation of certain alloying elements, such as phosphorus, sulfur, or other trace elements, at grain boundaries during the tempering process. This segregation can lead to reduced toughness and ductility, increasing the susceptibility to fracture under stress. When assessing materials for potential temper embrittlement, it is important to consider their chemical composition, heat treatment history, and operating conditions, as these factors can influence the degree of embrittlement experienced. Temper embrittlement is a phenomenon typically observed in certain steels and alloys, particularly those that have been tempered and then exposed to specific conditions. It is characterized by a reduction in ductility and toughness, which can lead to unexpected brittle fracture. Here are the critical factors that influence the temper embrittlement damage mechanism. Number 1 is temperature. The temperature at which the steel is tempered plays a crucial role. Tempering at certain temperatures can lead to the segregation of impurities, particularly phosphorus, at grain boundaries, which promotes embrittlement. Number 2 is chemical composition. The presence of specific alloying elements, particularly those that can segregate to grain boundaries, like phosphorus, sulfur, and certain transition metals, is a decisive factor. Higher concentrations of these elements can increase susceptibility to embrittlement. Number 3 is time at temperature. The duration of exposure to the tempering temperature can impact the extent of embrittlement. Longer exposure times may allow for more significant segregation of alloying elements to grain boundaries. Number 4 is prior heat treatment. The history of heat treatment, including quenching and the preceding aging processes, can influence how the material will respond during tempering. Previous microstructural features often dictate how susceptible the alloy will be to temper embrittlement. Number 5 is microstructure. The initial microstructure, e.g., martensitic, bainitic, or ferritic, and the size of grains can affect the overall likelihood of embrittlement. Finer microstructures may exhibit different behaviors than coarser ones. Number 6 is environmental factors. Exposure to certain environments, particularly those containing moisture or corrosive elements, can play a role in exacerbating temper embrittlement. The combination of embrittlement and environmental corrosion can significantly reduce the lifespan of a component. Number 7 is loading conditions. Stress states and loading conditions, including cyclic loading and stress concentrations, can also influence the likelihood of brittle fracture in embrittled materials. Number 8 is post-tempering treatments. Processes such as aging or retempering may reduce or mitigate the effects of temper embrittlement, depending on the conditions applied. Addressing these factors during the design and processing of steels is critical to avoid the detrimental effects of temper embrittlement and ensure the mechanical integrity of components made from these materials. Affected units or equipment. Temper embrittlement is a damage mechanism that primarily affects certain types of steel, particularly some high-strength low-alloy (HSLA) steels and certain types of carbon steels, particularly in the heat-treated condition. The affected units or equipment typically include: Number 1 is pressure vessels. Components designed to withstand high pressures may experience embrittlement, particularly in regions that have been tempered after quenching. Number 2 is pipelines and piping systems. Steel used in pipelines, especially those that have been heat-treated or alloyed, can be susceptible to temper embrittlement, leading to catastrophic failures. Number 3 is heating equipment. Boilers, heat exchangers, and other thermal systems can be susceptible, particularly when operated at high temperatures. Number 4 is structural steel components. Steel beams, columns, and other load-bearing components in industrial and commercial structures. Number 5 is forged and machined parts. Components such as gears, pins, and fasteners made from alloyed or heat-treated steels. Number 6 is high-temperature operating equipment. Equipment operating at elevated temperatures such as furnaces, kilns, and reactors. Number 7 is welded components. Welds in heat-treated steel can be particularly vulnerable to embrittlement, affecting the overall integrity of the welded assembly. Temper embrittlement generally occurs when certain alloying elements, like phosphorus, antimony, and tin, segregate at the grain boundaries during a prolonged exposure to elevated temperatures, usually in the range of 250 degrees Celsius to 600 degrees Celsius, 482 degrees Fahrenheit to 1112 degrees Fahrenheit. This can lead to a marked decrease in toughness and ductility, making the affected units more prone to brittle fracture under stress. To prevent temper embrittlement, careful selection of materials, control of processing temperatures, and the use of lower phosphorus steels can be employed in design and manufacturing practices. Regular inspections and maintenance are also vital in detecting and mitigating this damage mechanism in affected equipment. Appearance or morphology of temper embrittlement damage mechanisms. Based on API 571. The first is temper embrittlement is a metallurgical change that is not readily apparent and can be confirmed through impact testing. Damage due to temper embrittlement may result in catastrophic brittle fracture. The second is temper embrittlement can be identified by an upward shift in the ductile to brittle transition temperature measured in a Charpy V-notch impact test, as compared to the non-embrittled or de-embrittled material, Figure 4, 5. Another important characteristic of temper embrittlement is that there is no effect on the upper shelf energy. And the third is SEM fractographs of severely temper embrittled material show primarily intergranular cracking due to impurity segregation at grain boundaries. Temper embrittlement is a type of damage mechanism that occurs in steel alloys, particularly those with high nickel and manganese content. The appearance or morphology of temper embrittlement damage can be described as follows. Number 1 is intergranular fracture. Temper embrittlement typically manifests as an intergranular fracture, where the crack propagate along the grain boundaries of the steel. Number 2 is river-like pattern. The fracture surface often exhibits a characteristic river-like or rock candy pattern, with a network of intergranular cracks and tears. Number 3 is dimples or voids. The fracture surface may also show dimples or voids, which are indicative of localized ductile failure. Number 4 is grain boundary decohesion. In some cases, the grain boundary may appear to be decohered, with a smooth, flat surface indicating a lack of cohesion between adjacent grains. Number 5 is no significant plastic deformation. Unlike other types of embrittlement, temper embrittlement often occurs with little or no significant plastic deformation, resulting in a relatively flat and featureless fracture surface. Number 6 is fracture path. The fracture path may follow the prior austenite grain boundaries, which can be revealed by etching the sample with a suitable etchant. Number 7 is microscopic features. At the microscopic level, temper embrittlement may be characterized by the presence of thin films of precipitates, such as phosphides or carbides, along the grain boundaries. It's worth noting that the exact appearance of temper embrittlement can vary depending on the specific steel alloy, heat treatment, and environmental conditions. A thorough examination of the fracture surface using techniques such as scanning electron microscopy or SEM and energy dispersive spectroscopy or EDS may be necessary to confirm the presence of temper embrittlement. Temper embrittlement is a type of intergranular cracking that occurs in certain steels, particularly those with high nickel and copper content, when exposed to certain environmental conditions. The primary prevention and mitigation methods for temper embrittlement damage include: Number 1 is material selection, choosing steels with lower nickel and copper content, as well as those with a balanced composition to minimize the risk of temper embrittlement. Number 2 is heat treatment. Proper heat treatment procedures, such as slow cooling and proper tempering, can help to minimize the risk of temper embrittlement by controlling the microstructure of the material. Number 3 is welding and joining techniques, avoiding the use of high-heat welding techniques and using techniques like laser welding, friction stir welding, or electron beam welding that produce less residual stress and heat. Number 4 is post-weld heat treatment, applying post-weld heat treatment or PWHT procedures, especially for high-risk welds, can help to relieve residual stresses and reduce the risk of temper embrittlement. Number 5 is environmental controls. Maintaining a clean, dry, and low-salt environment can help to minimize the risk of temper embrittlement. Number 6 is reducing stress levels. Keeping stresses on the component as low as possible through proper design and installation can minimize the risk of cracking. Number 7 is using inhibitors. Using inhibitors in corrosive environments can help to mitigate the effects of temper embrittlement. Number 8 is monitoring and inspection. Regular monitoring and inspection of components, especially those prone to temper embrittlement, can help to identify and prevent damage. Number 9 is design consideration. Designing the component with a suitable factor of safety and taking into account the potential service conditions can help to minimize the risk of temper embrittlement. Number 10 is material certification. Ensuring that the material used meets strict standards and certifications can help to minimize the risk of temper embrittlement. By following these best practices, you can reduce the risk of temper embrittlement damage and ensure the reliability and performance of your components. Inspection and monitoring for temper embrittlement damage mechanisms. Temper embrittlement is a phenomenon that can affect certain heat-treated steels, particularly those that have been tempered at elevated temperatures. It is caused by the diffusion of elements like phosphorus and molybdenum during the tempering process, leading to a reduction in toughness and increased susceptibility to fracture. To detect temper embrittlement damage, various inspection and monitoring methods can be employed, including: Number 1 is mechanical testing that divided by 3, but not limited to the following. The first is Charpy impact test. This test measures the energy absorbed by a material during fracture and helps assess the toughness of the steel. A reduction in toughness can be indicative of temper embrittlement. The second is tensile testing, determines yield strength and ductility, which may be affected by temper embrittlement. An increase in yield strength with a decrease in elongation may signal embrittlement. And the third is hardness testing. While not a direct measure of embrittlement, changes in hardness can indicate alterations in microstructure due to temper embrittlement. Number 2 is metallographic examination that divided by 2 but not limited to the following. The first is optical microscopy. Examining the microstructure of the steel samples can reveal changes in grain size and microstructural features associated with temper embrittlement. The second is scanning electron microscopy. SEM provides a detailed view of the fracture surface and microstructural details, allowing for analysis of secondary phases or segregation patterns that could indicate embrittlement. Number 3 is non-destructive testing, commonly called NDT, that in this case divided by 3 but not limited to the following. The first is ultrasonic testing. This method can detect internal flaws and assess material properties without causing damage. Changes in sound propagation characteristics can indicate embrittlement. The second is eddy current testing, measures changes in electrical conductivity and can provide insights into material condition. And the third is magnetic particle testing, commonly used for surface defects. This technique can help identify potential flaws that may be exacerbated by embrittlement. Number 4 is chemical analysis. Spectroscopy. Techniques like X-ray fluorescence or XRF or optical emission spectroscopy or OES can quantify the presence of elements like phosphorus and molybdenum, which are critical to the temper embrittlement process. Number 5 is service monitoring. The first of service monitoring, long-term performance monitoring. Observing performance and failure characteristics of components in service can inform about the onset of embrittlement over time, particularly in high-temperature applications. The second of service monitoring is regular inspections. Implementing a routine inspection schedule for components known to be susceptible to temper embrittlement can aid in early detection of damage. Number 6 is thermal history evaluation. Analyzing the thermal history of components that may have experienced tempering at elevated temperatures can help predict susceptibility to temper embrittlement. Number 7 is fractography. Analyzing fracture surfaces from failed components can provide insights into the failure mechanisms, aiding in the identification of temper embrittlement behavior. Proper application and combination of these methods can help detect and monitor temper embrittlement damage effectively, contributing to better material reliability and safety in engineering applications. Thank you.